Well, it's an exciting day because we're finally to the last problem set number 6. So we're going to be doing some integration right now. These first two examples are going to help you out with page 1 of problem set number 6. So with this first one right here, it looks like it's quite a mess, but if you use U-Substitution, you could simplify it quite a bit. And you let the U equal what's inside the parentheses. So u equals 1 over x. And then that's one of those derivatives that I have memorized. The derivative of 1 over x is negative 1 over x squared. And then times dx. So notice this has dx on the top, x squared on the bottom. This also has dx on the top and x squared on the bottom. So it matches up perfectly, other than the negative sign. So just multiply both sides by a negative 1, and then it's ready for the U-substitution. So this would become secant squared, and then inside the parentheses, that's just going to be u. And then this x squared and dx gets replaced with negative du. And for the negative, I'll just put it on the outside, factor out to negative 1. So that definitely simplified the problem. Now I just have to think, what's the antiderivative of secant squared? Well, the derivative of tangent is secant squared, so that means that the answer is going to be negative tangent of u. And then plus the constant c. The last thing to do on this one is replace the u with 1 over x, and then we're finished with number 1. Okay, then on to number 2. So for example number 2, estimate the integral from 1 to 4 for the square root function using the midpoints of 10 rectangles. So the idea is that we have an interval going from 1 to 4, and we're going to break that up into 10 equal pieces. So first, find out what delta x equals. So you subtract 4 minus 1. So that's a 3. That's basically saying this is a length of 3. And then divide that into 10 equal pieces. So that will be 3/10, or I could use the decimal 3/10. So that means that the first interval is going to go from 1 to 1.3. And the last interval, if you subtract 0.3 from a 4, that's going to be a 3.7. Now we need the midpoints. So what's in the middle of a 1 and a 1.3? So perhaps you could just look at that and say it's 1.15. That'd be cool if you could do that. Otherwise, you could just take the two numbers, the 1 and the 1.3, add them together, and then divide by 2. Or in other words, find the average. And then for a 3.7 and a 4, find the average, 3.85. And then we're going to add up 10 rectangles. Of course, I'm going to have the calculator do that using some sequence. And you should go ahead and write this part down so that you show all of your work. We need the function, which is going to be the height of the rectangle, and then times delta x, which is the width of each rectangle. Then tell the calculator that x is the variable. It's going to start at 1.15, end at 3.85, and go in increments of delta x. So this last number is always the delta x. So then, using the calculator. So you go to second list, move over to math, and number 5 is the sum. And then second list, go over to operations, and number 5 is the sequence. So I have an old problem left over, and let me just erase that. So the expression is this part right here, the square root of x times a 0.3. And then x is the variable, and it starts at 1.15, goes to 3.85, and the step means the delta x, 0.3. And then it says that the answer is 4.688. Now I just want to see if I did that correctly. So what I'll do is I'll graph the original function, the square root of x, and then have the calculator integrate from 1 to 4. So go to second calculate. Number 7 is integrating from 1 to 4. And it says the actual answer is 4.667. I got 4.688. So this was my estimate. And the actual answer would be a 4.667. So my estimate was actually pretty decent, considering I only used 10 rectangles. Okay, then on to page 2 of the problem set. So this is going to be called example number 3 right here. And suppose that we stick with that same function, the square root of x, on the interval from 1 to 4. So with this, we're just going to set up the integrals. If this shape right here, on the interval from 1 to 4, is rotated about an axis, then it becomes a three-dimensional object. Find the volume of that three-dimensional object. And you only need to set up the integral, not actually work out the problem. So part A, rotate about the x-axis. So I like to visualize what's going on. The square root function looks like this. From 1 to 4 is this area right here. And then rotate that about the x-axis. So I'm going to set up my representative rectangle this way. So that way it's going from the x-axis to the function itself. So it always needs to go between two functions, the x-axis and then the function. If I put it sideways, the problem is sometimes it would be going from 1 to 4, and by the time I got up here, it would go from the function to 4, so I would have to set up two integrals instead of just one. So it's better to set up the representative rectangle this way. So when the axis of rotation and the representative rectangle are perpendicular, then that is the disk method, or it could be the washer method. But this one has no gap in it, so it's not the washer, this is the disk method. And for the disk method, the formula is integrate pi r squared. So this one is going to be integrate pi, and r means radius. Radius is measured from the axis of rotation to the object. So in other words, what's the height of this rectangle? Well, the height is just going to be the square root of x function. And x is going from what to what? So this rectangle would start over here at 1, and then move over and move over, move over until it gets to 4. So we integrate from 1 to 4. And since I said just set up the integral, that one is finished. Then for the next one, what if we rotate about the y-axis? So it's the same shape. So I think I'll save a little bit of ink, and no, I think I'll go ahead and spend the ink. So it's the same shape going from 1 to 4. So it's this shape. And then rotate that about the y-axis. So again, I would like to set up the representative rectangle this way. That way it's always going from the square root function to the x-axis. Now when the representative rectangle and the axis of rotation are parallel, that you have no choice. That's the shell method. And the general formula for the shell method is you integrate 2 pi times the radius times the height. So this is going to be, let's see, the radius has to be measured from the axis over to the rectangle. So in other words, what is this length right here? Well, if x is going to go from 1 to 4 at any given moment, this is x. So x could equal 1 or 1.5 or 2, etc., etc. But this length, that will be a length of x. So that's the radius. The height is the height of the rectangle, which will be the square root function. And then integrate with respect to x. And again, x would go from 1 to 4. And since it said just set it up, that one is finished. And then how about part C, rotate about x equals 5. So the same shape. This goes from 1 to 4. This is the shaded region. And then x equals 5 is this vertical line right here. So rotate about that vertical line. And like on the other ones, I'm going to make the representative rectangle vertical. And like the last one, this rectangle and this line are parallel to each other, so there's no choice. It's going to be the shell method. So integrate 2 pi times the radius times the height. Now the only difference is what's the radius, because the height is going to be the same thing as last time. The limits are going to be the same thing. The only thing that changes is the radius. Well, like I said on the last one, if you measure from here to here, that's a length of x. But if you go from 5 over to here, because the radius has to be measured from the axis of rotation over to the rectangle. So the r has to be measured this way. Well, if it's a 5 that's on the right and it's an x that's on the left, then this length right here would be 5 minus x. That way, when you add up this one plus this one, it's a total length of 5. So that's the r. So this one will be integrate from 1 to 4, 2 pi. The radius is 5 minus x. The height is the square root of x. And then that one is set up. Okay, so that was for help on page 2. Now, one last example. This would be example number 4. Look at this one. Integrate from 1/2 to 1 the square root of 1 minus x squared over x squared. And if you try U-substitution or algebra or any other method, you're probably going to get stuck. So I'm going to add in u's that x equals cosine of theta. So that part is given, part of the given problem. All right, so that means that I could substitute a cosine in for this x, and I could substitute a cosine in for this x. But I also need something to substitute for dx. So take the derivative. The derivative of cosine is negative sine of theta, and then times d theta. Now the other thing is the limits are going to change because this is what x equals and this is what x equals. So I should plug that in right here and then find out what does theta equal, because I'm going to change this problem into a problem with thetas instead of with x's. So if x equals 1, you would say, when does cosine equal 1? Well, the cosine graph goes like this. And so cosine equals 1 when theta equals 0. Then when does it equal a half? So a half would be right here. That would be right there. So just by looking at the graph, I'm not sure what it is. I forgot to write it down. 1/2 equals cosine of theta, and I can't tell by just looking at the graph. So then I just need to take cosine inverse of a half. So what is, clear that out, what is cosine inverse of a half? That looks like it's pi over something. So to find out if it's pi over 5 or pi over 6, whatever, divide by pi, and then go to math and change that to a fraction. So it's 1/3 of pi. So it's going to be pi over 3. So in place of the 1, then I'll be using 0. And in place of the half, I'll use pi over 3. So what's this going to look like? All right, so in place of the half, use pi over 3. In place of x equals 1, we're going to use theta equals 0. And then this part is going to be 1 minus, and replace x with cosine, so that's going to be the square root of 1 minus cosine squared. And on the bottom, it's just going to be cosine squared. And then in place of dx, we need to use this, negative sine of theta times d theta. So the negative, I'll just factor out, and then it'll be sine of theta, d theta. Now we need to use trig identities. 1 minus cosine squared is equal to sine squared. Then take the square root of that sine squared, it's going to be a sine. So this whole square root thing just becomes sine. Then it's times another sine. So sine times sine means we've got sine squared in the numerator and cosine squared in the denominator. Well, sine divided by cosine is tangent. So that means that this one is actually tangent squared. Then, how do you integrate tangent squared? Well, if you think about the derivatives, the derivative of tangent is secant squared. That's not secant squared. The derivative of tangent is secant times tangent. That's not correct either. So, and if you tried U-substitution, you should let U equal tangent. And the derivative of tangent is secant squared, and there's still no secant squared in this problem. So then we could use a trig identity. So over here, I'm going to write down the trig identity I know is that 1 plus tangent squared is equal to secant squared. Or if you subtract 1 from both sides, tangent squared is equal to secant squared minus 1. So this could be replaced with secant squared minus 1. All right. Now, what's the antiderivative of secant squared? Well, the derivative of tangent equals secant squared, so that works out perfectly for this one. So it's going to be minus, and then the antiderivative of secant squared is tangent of theta. And the antiderivative of a 1 is going to be theta, because theta is our variable, not x. And then that needs to be evaluated from pi over 3 to 0. And don't forget the negative sign right here. So then I just need to finish that over here. So there's the negative sign, and then there's, substitute the top number first. So tangent of 0 minus 0 minus parentheses tangent of pi over 3 minus pi over 3. Well, tangent of 0 is 0, so that's a 0 and that's a 0, so those two disappear. And then this negative and this negative could cancel each other out after these guys disappear. So all that's left is, after these two negatives cancel, what's left is tangent of pi over 3 minus pi over 3. And how much is that? So it's in radians, that's good. Tangent of pi over 3 minus pi over 3. So it equals a 0.685. All right, I hope this helps with problem set number 6.